Hey, physics student. In this lesson, I'm going to show you how to use energy conservation to calculate an object's speed. Speed is also called velocity, and so we're going to kind of use speed and velocity interchangeably. We're going to, they kind of mean the same thing here. I would like to show you two examples. Make sure that you write each example in your notebook. After I'm done, you can go ahead and use the examples, and you can use them to help you do some more practice. All right, so the first example I'm going to do is going to just involve a picture of an object going down a ramp. So in my notes here, I'm going to draw kind of a triangle to represent a ramp. Something like that. Okay, and the object itself, I don't know, I'm just going to put, let's say it starts up at the top of the ramp, and I'm going to label this up here point A. So that's point A. And it's going to start up at the top of the ramp, and then it's going to slide down this ramp. And let's say when it gets down to the bottom, when it's at the very bottom, we're going to call this point down here point D. Okay. And so the goal is if you release the object from A, we want to figure out how fast is it moving at D. Okay. So so that's the idea with this. Okay. Now things that we need to know that might be important would be things like how high is point A, what's the height, and is the object moving at point A, right? Or is it starting from rest? So I suppose let's just start talking about those things right now. Okay. So first of all, how high is point A? So I'm going to just kind of, in my triangle, I'm going to highlight this. Okay. And that height, I'm going to make up a number here. Let's say that it starts moving from a height of 5 meters. Okay. I'm also going to say at point A that the object starts at rest. So that means that its speed or its velocity would be equal to 0 meters per second. So those are important pieces of information, right? The height is going to tell us about potential energy at A, and the velocity will tell us about kinetic energy at A. Now, when you go down to the bottom of the track, we also need to know what about height and velocity. Okay, so at the bottom of the track, the height down here, of course, looks like it would be 0 meters. And so, yeah, we're going to use the ground as a reference level, which is pretty typical. Now, the velocity at D, right, how fast is the object moving? I'm just going to put V equals a question mark because that's what we want to know. So the goal, I'm going to circle this, right? The goal of what I'm about to show you is how can you find that value of the velocity. All right, so before we actually do the math, let's sketch a quick bar graph to show what the energy is doing here. So I'm going to have a bar graph here. Let's see, I'm going to draw 1, 2, 3 lines there, and then I'm going to do another 3 over here. So leave space in your notes for something like that. Okay, and the idea would be is that I'm going to track kinetic energy, KE, potential energy, PE, and total energy, TOT. And I want to do that for both point A, and I also want to draw a bar graph for point D. Okay, so let me copy that down. So again, KE, PE, and total. Okay. So before I actually do any math or anything, it's really helpful to kind of imagine energy bar graphs and what's happening with this. Okay. So let's take a look at A. At A, we said the object is not moving. And if it's not moving, its kinetic energy is actually just 0. So I'm going to highlight that in red. There's really nothing to draw there, right? Because the kinetic energy is 0. However, at A, the object is really high up in the air. So it's going to have some potential energy. So I'm just going to kind of randomly do like maybe 4 blocks. And so that's the potential energy. And so that means at point A, all of the energy is potential energy. And if I add these two things together, if I add 0 plus that, I get my total energy, which is going to be exactly the same as the potential. All right, so hopefully this looks familiar to you when we did this, the bar graphs in PhET. All right, now let's look at D, right? So kind of going over to D. So this is going to be a separate bar graph. Yeah. I hope you agree from what you've learned about physics that at D, the potential energy is 0, right? Because the object is at ground level, the height is 0. And so the idea would be that at D, we want to know about the kinetic energy because that's going to help us to find the velocity at that point. And the thing that we know, that we've learned, is that the total energy at D, whatever it is, that total energy had better be exactly the same as what it was when you started. So the total energy has to be the same. And the potential energy is 0, and that means that all of my total energy is now in the form of kinetic energy. So just kind of visually, right? If I add together lots of kinetic here, plus 0 potential, I end up with the same total energy that I started with. And so this bar graph is very important because it's going to help us to write the equation that comes next. All right, so take a minute if you need to, finish that up, and then let's write an equation. So now I'm going to, underneath this, write an equation that's based on my graph. Okay, I'm going to write an A part. All right, so I'm going to put the E total at A, and it better be equal to the E total at D. Sorry, that's kind of messy, but you get the idea, right? And so at A, let's see, I don't have any kinetic energy. My bar graph says there isn't any, but I do have potential energy. Okay, that adds up to a total. So my bar graph is telling me that the first term is 0 for kinetic energy. The second term is not. And then if I look at the D part, I can see that I do have kinetic energy at D. So I do have KE, but I do not have potential energy. So I'm putting a 0 there. And that's it. All right. And so my potential energy at A is equal to my kinetic energy at D. And so now what I can do is I can just kind of plug in formulas. So I've got, for potential energy, mass times gravity times the height at A. Actually, we don't even need to write that if you don't want to. So just mass times gravity times height, and that's equal to 1/2 times mass times velocity squared at D. Okay. And then we can go ahead and we can solve it. So now we've used our bar chart, we've used it to write an equation, and now we can solve it. So we need some information here. I never told you the mass of the object. Let's just write that up here. So the mass, let's just say it's equal to 2 kgs. And so now I can plug in my numbers here, and I've got 2 times 9.8 for G. And my height at A is 5 meters times 5. I'm going to leave the units out. So 2 times 9.8 times 5. Fix that up. And then that's got to be equal to 1/2 times the mass. The mass is 2 times V squared. And remember V is the thing that we wanted to find out what is V. And so we need to get the V here. We're going to solve for it. So this is an equation, and that's the unknown. Okay, so let's continue. So now in my calculator, I'm going to calculate 2 times 9.8 times 5. So I'm going to do that on my calculator. 2 times 9.8 times 5. That would be 98 joules. And then over here, I've got 1/2 times 2. That's 1 times V squared. Okay. And so then I've got that over here. So I'm almost done. So basically what I have is 98 is equal to 1 times V squared. So to find the velocity, the last step I have to do is I have to take the square root of both sides, right? And so I would take the square root of 98. Now, there's a 1 in front of that, and I would really have to divide this 1 over, but I guess we don't really need to do that, do we? But you do have to take the square root. of 98. So if I take the square root of 98, I get, let's see what I get here. I get something close to 10, I hope, right? That comes out to be 9.9 meters per second. And that is the answer, okay? So the technique here is pretty important, right? We started off with a sketch, and our goal was to find the velocity at some point on the track. We used our physics knowledge to kind of sketch some bar graphs for point A and point D, kind of your starting point and your ending point. And then from our bar graphs, we actually wrote this equation down here for energy conservation. Okay, so this is energy conservation happening here. That's E conservation. And we use the formulas, right? The formulas that we learned earlier in class. And we went ahead and we just kind of plugged in the numbers. Hey, something you might have noticed this, is that look at the number for the mass that we used. That number 2, you see how it shows up in both places? Yeah, so the fact that it shows up in both places means that really it doesn't matter at all. And maybe in the second example I can prove that to you, but we can pick a different mass and you'll get the same answer. So like, it's kind of neat. The mass, it factors out. So I think we saw that, you guys saw that when you did the PhET simulations. If you changed the mass of the skater, it didn't affect the skater's speed at all. So, right. So if you want to use the mass in the calculation, go for it, but you really don't need to. Okay, so that's example 1. Let's do example 2, slightly more complicated, just a little bit. I'm going to try to go a little bit faster here. And I'm going to draw a triangle again for a ramp. But this time I'm going to pick points which are kind of like here and here. In other words, I'm not starting from rest. Okay, the object is going to be rolling down this or moving down this ramp a little bit. Let's call this point B. We'll call this point C. Okay, so it's moving. It's got a little bit of speed there. But the goal is we want to find out how fast is it moving at C. Okay, so let's put some numbers into this. So we need to know the height. All right, I'm going to say my height here is 4 meters. And for the initial speed of B, like where it's moving, I'm going to say that velocity is 4.4 meters per second. Okay, so it's moving, right, at this point. So it's going to have kinetic energy and potential. At point C, it's going to have a little bit of height. Let's make this 1 meter. And the goal is to find out how fast it's moving. And so I'm going to circle the velocity here. We want to find out how fast it's moving. All right, so let's do quick bar charts here. Again, six dashes here. 1, 2, 3. Then 1, 2, 3. This will be at point B. This is at point C. I'm going to keep this super simple here. I'm just going to put K and P and T, right? Kinetic, potential, total. Same thing, K, P, T. And so now I have to think carefully here, because when I look at point B, I can see it has some kinetic energy. So there's going to be something there. I don't know how much, but something. I also see that at B, it's still up pretty high. It's 4 meters. So maybe it's something like this, right? Probably more potential energy than kinetic. So at point B, I've got 2 kinds of energy. When I add them together, like in my example, I have 1 block and 3 blocks. Those would add up to 4. So that's what my bar graph looks like. Okay. So when I jump to point C, I automatically know by energy conservation that my total energy has to be 4 blocks. But there's got to be some trade-off here, right? Because now a lot of potential energy that I used to have has been changed into kinetic. So there's going to be some kind of switching around, right? And I don't know if this is exactly correct, but I'm going to say It's probably something like this, right? Where I'm going to end up with more kinetic and less potential at C. So those numbers might not be perfect, but at least it kind of gets me thinking the right way. Okay, we're going to finish this then. We're going to write an equation now. So the energy at B is equal to the total energy at C. And in this case, I'm going to have kinetic energy at B and potential energy at B, right? Because neither one of them is 0. And then the same thing over here. I have kinetic energy at C and I have potential energy at C. Okay. And then we just go ahead and we're gonna put our formulas in. So for kinetic energy, I'm gonna have 1/2. Okay, and then for a mass, I'm gonna make up a different mass here just to be crazy. Let's just say the mass of the object is 5 kg. Okay, so I'm gonna have 1/2 times 5 times the velocity of 4.4 squared. So that's the kinetic energy at B. And then for potential energy at B, I have mass times gravity times height. So I'm going to have 5 times 9.8 times the height of 4 meters. Okay, I'm going to do the math on that right now. So 1/2 times 5 times 4.4 squared is 48.4. And on the other, for the potential energy, 5 times 9.8 times 4 is 196. So that's the energy that I have at point B. I'm going to add those numbers up. That gives me a total energy of 244.4. Okay, so that's the energy at B, the total energy. At C, let's now focus on these terms. So the kinetic energy at C is going to be 1/2 times the mass, which is 5, times V squared. That's the thing we want to know, right? That's this guy right here. So I don't know, I put a variable. And then I do plus mass times gravity times height plus mgh. So plus 5 times 9.8 times the height of 1. Okay? So that's the other side of the equation. All right, so now on my calculator, I'm going to work this out. So 1/2 times 5, that's 2.5 v squared. And then 5 times 9.8 times 1 is going to be 49. Okay. So that's what I got. Now I'm going to just copy that down again because now I just have to solve it. But I've got to be careful about my steps, right? All right, so that's my equation. I'm almost done. I want to solve for velocity. And the way that you solve for velocity is the first thing you do is we're going to subtract 49 from both sides. And that will get rid of it here. So 244.4 minus 49 gives me 195.4. And then I just carry down 2.5 v squared. Okay? Then the last step I'm going to need to do is I'm going to need to get rid of the 2.5, and I do that by dividing. I have to divide both sides. And I hope you can see that that cancels here. But on my calculator, I take 195.4 divided by 2.5, and I get 78.16. Okay, now that's not the answer yet because I still have a v squared here. And so my last step, I have to take the square root. Okay, so if I square root this side, I have to square root that side. And so that's going to give me V is equal to the square root of 78.16. And the answer here is 8.8. We'll just round it off to that, meters per second. And that's it, okay? So this example had more math in it, didn't it, right? And it did because it was more complicated, because you started off moving, and when you ended, you weren't all the way to ground level. So, you know, this is one way you can go about solving this problem. You might discover there are some shortcuts here, and feel free to use them as long as you understand what you're doing. But this technique should work for anything. So in today's practice assignment, you're going to try PhET, and you're going to try to basically just use different track shapes and use the tools to figure out what's going on. So in PhET today, it's going to be like this. You're going to go to motion. Oh, I don't know if you can see this anymore. So I think you might not be able to see this particular screen. So anyway, the directions for the PhET activity are on your table today. So try it out, and good luck with getting some good answers.